figure out what you did wrong and let me know if you're not sure. If you have some confusion on what the answer key is saying and you don't understand, just during break, Math Center, wherever, seek me out and I can help walk you through any of that stuff that you don't quite understand from the answer key. So super important going forward that all these classes sort of build, even if the specifics aren't used again, there's stuff that builds repeatedly. Bottom of my pack here. So figure out what you did wrong because the final exam's cumulative, so a bunch of that stuff's coming back again. It's not going away. And integration techniques are super important when you get to Calc 3. Calc 3, you're going to be dealing with double and triple integrals, which is basically, like a triple integral is really just 3 one-variable integrals. They're just stacked inside of each other. So you've got to get this whole integration stuff doesn't go away. It just gets worse. So you want to make sure that you figure out what you did that wasn't exactly right because you want to be a good integrator. Let's see. There is a pen right there. Okay, so look at that key and let me know if you have any questions on it. We are going off to chapter 10, the Gauntlet, Sequences in Series, chapter 10 and 11. This book breaks it into 2 chapters. Most books actually do it in 1. We sort of think of sequences in series as kind of a big package. We will first cover 10.1, which gives us a brief overview of sequences and a brief overview of series. And then we'll get into the details when we get to 10.2 and 10.3 and beyond. So this topic is, this looks odd. This topic is, we're going to start from scratch with this idea of a sequence. And let's see, is something fishy happening? So this is notation. So we want to start with this idea of a sequence, and then we'll go from there. And a sequence in math is just an ordered list. It's an ordered list of numbers. Notationally, we use the curly brackets or the braces, and we index our terms, usually starting at a 1. So a sub 1 is the first term in the sequence. A sub 2 is the second term in the sequence. So usually that's how we're going to index it. It is possible to start with 0 as your first term. It does not matter how you index, if you want to start at 0, if you want to start at 1. Ideally, we start at 1 so that the 10th term has a 10th number as the index. It's just easier. But mathematically, there are times where it's going to be a lot easier to start with 0. We'll see when and why that might be. Doesn't matter. So there are 2 ways in math that we generate sequences. One is with a recurrence relation, and there's a very famous sequence that you've all heard of that's generated with a recurrence relation. In other words, we find the subsequent term by doing something to the prior term or terms. So you get to the 10th term by looking at the 9th term. You get to the 12th term by looking at the 11th term. You do something to the prior term. So that's a recurrence. Anyone know what that most famous of all recurrence relations is?
Golden ratio? The harmonic series?
What was that? Fibonacci. Fibonacci sequence is the most famous recurrence sequence. Golden ratio, I believe you can set up a recurrence relation, but I don't know what it is off the top of my head. But yeah, I think you're right. I think you can set up a recurrence relation. But the most common one that we hear about is the Fibonacci sequence. That's use the 2 prior terms added together to get to the next term. Starts with 1 comma 1, the next term's 2, the next term's 3. You just add the prior 2 terms to get to the next term. So that's how You set up a recurrence relation. Those we are not going to look at very much. For us, the second way of generating a sequence using a formula is going to be the more common method of generating a sequence for us. That's more practical in the real world. That sort of describes things more more commonly. And so what we mean is that we are going to find the nth term by doing something to its index. So a sub 1's value will be dependent on the 1. A sub 7's value will be dependent on the 7. A sub 12 will be dependent on the 12. So the index is what's going to guide us. And we call this notation functional notation, right? This says that the nth term is a function of n. And we know functions, pass the vertical line test, and we know how to do a whole bunch of stuff with functions. The big difference here is that this function is discrete. It's a set of points. The domain is the set of positive integers. So, there's no continuum, right? There's just dots. There's a dot at 1, a dot at 2, a dot at 3. So those indices are going to be corresponding to x values if we graph. So notationally, we can sort of list out the terms in a sequence like that. Sometimes we write this, almost never. It's too much writing. Usually we just go with that. Curly braces, a sub n means the sequence a sub n. And, it's usually from the context you can tell whether either n starts at 1 or starts at 0 or some other number. Usually from the context you can tell. So this just summarizes what I said about a sequence being a function. So if a sub n is found by doing something to its index, the sequence is a function. The domain is usually a set of positive integers, but it could be slightly different depending on the sequence. So that is the heart of what a sequence is, just an ordered list. So here is a picture of a common sequence. This one is called the harmonic sequence. The harmonic sequence is just the reciprocal function with positive integer domain. So I will put a lot of the Desmos stuff in here just in case you want to play with Desmos. Desmos is great for sequences in series. So the superset, or the continuous version of this function, is 1 over x. So 1 over x is graphed with the dashes, and then 1 over n is a subset. So 1 over n is a subset, and so I graphed it as n comma a of n, where a of x is defined to be the continuous function. So then the sequence is a subset. So the sequence is a subset of the continuous curve. You can think of the continuous curve as a superset of the sequence. So sequence is embedded within the continuous function. Okay. And we can see clearly that the limit of this sequence is, where do those terms go as n goes to infinity? 0, right? So that was the first basic limit that you learn in Calc 1, is that if you have a constant numerator and the denominator is going to infinity, the fraction values are going to 0. That was your first basic limit in Calc 1. That's like a building block limit. Limit of 1 over n, 1 over x, whatever. As the denominator goes to infinity, the fractions go to 0. And we can see that graphically here. The limit of this sequence is the y value that the terms are getting closer and closer to. The y value that the terms are getting closer and closer to is 0. So, limit of a sequence is exactly what we just said. So, for the limit of a sequence to exist, let's suppose that that sequence converges to L. As n gets bigger and bigger, as the index grows, the terms get arbitrarily close to that L value if the limit is going to exist and be L. It gets arbitrarily close. As you go further out in the sequence, it gets tighter and tighter, closer and closer to L. L is a y value. So if that's true, We say that the limit of the sequence is L. We say the sequence converges to L. And if the terms do not approach a single number, then we say the sequence diverges. So when we look at something like the limit of, let's just say n, as n goes to infinity, this sequence, we would say that. It diverges. We say n, the limit of n is infinity. That doesn't mean the limit is existing. We just have to be careful with the notation. We typically translate the equal sign as is. And so this sort of says the limit of n as n goes to infinity is, the limit of n as n goes to infinity is infinity. But this doesn't mean the limit exists. We should probably use a different symbol here when the limit does not exist. When we write this equals infinity, we're describing how the limit doesn't exist. The numbers are getting bigger and bigger and bigger without a bound. They just keep getting bigger and bigger. So this limit does not exist. So it would be correct to write this. You could write that this is your conclusion. But usually we would write that. This is better because it describes how the limit doesn't exist. So the main point is if the sequence terms are not getting closer and closer to a single number, then the sequence has no limit, then the sequence diverges. All right, so the limit of the harmonic sequence is 0. Here's a picture of the alternating harmonic sequence. With sequences in series, there's a lot of times where we're going to throw in this piece, this little factor that we call a switch. It could be -1 to the n, or it could be -1 to the n plus 1. It just kind of depends on whether you want the even indexed terms to be negative or the odd indexed terms to be negative. So if you throw in that switch, that is just going to change every other sign. So it'll be plus, minus, etc., or minus, plus, etc. So there's what the alternating harmonic looks like. Again, there's our 1 over x is the dashed, and then I built the bouncing function. We can still see that the limit is 0. Yeah. The terms are still getting closer and closer to a single y value, 0. So we're getting arbitrarily close to 0. So we say that the limit is 0. And this is still sort of one of those basic limits. The numerator is a constant. It's 1 or it's -1, depending on the value of n. But that doesn't matter. If you have a constant in the numerator, whether it's positive or negative, if the denominator is growing without bound, then the fractions have to go to 0. Whether it's a -1 or a +1 or alternating, it does not matter. The limit will be 0. And again, this little factor here that switches the signs, generally we call it a switch. Since it's switching the signs. Okay. So let's take a look at some specific examples. They tell us that we have some terms of a sequence where the index starts at 1, goes to infinity, and they first want us to find the next two terms of the sequence, and then we want to describe this sequence with a recurrence relation, and then describe it with an explicit formula, so as a function, so both ways. Pretty obvious how to get the next terms, right? So the next terms here, we are going to start with our 4 terms here. Clearly, we are adding 3. So we're going to have a 14, and then a 17, and etc. So those are the next 2 terms. Now the harder stuff. So let's go with B first, where we want to do a recurrence relation. So with a recurrence relation, we define the next term from the prior term, and we need to be given some initial value. We need to know where we're starting. Well, we're going to say that a sub 1 is 2. That's where we're starting. A sub 1 is 2. And now we need to indicate how to get to a sub 2, a sub 3, etc. So we will say that a sub n plus 1 is going to be the prior term, which will be a sub n, plus what?
3.
Plus 3. So this is how we get to the subsequent terms. So to get to a sub 2, we're going to take a sub 1 and add 3. Well, we were given that a sub 1 is 2, so that puts it at 5, and then we get a sub 3 by adding 3 to a sub 2, etc. So that's a recurrence relation definition to generate that sequence. Part C, and one of the things we'll see with sequences is that often it's easier to describe the sequence in one way or the other. So this was really easy to describe as a recurrence relation. Let's see if we can describe it as a function. And so here is my strategy. So first, I'm going to think about the terms, and I'm going to try to figure out a pattern based on the index value. So the terms, I'm just going to stack them right over here. And this is a really good, I've done some work with prime numbers and looking for patterns. And you can do this kind of thing in a spreadsheet. You know, you can just make your columns functions of the prior column, which is kind of cool. So here's where we're starting. Those are the numbers we want to generate. And we're going to look at our index values. So we want to generate those. Our index values are as follows. And so we want to use that index, those indices, to get these a sub n's. And it's almost never obvious. Like looking at that, you don't just say, oh, I know how to get to 8 from 3, and if you do figure out a way to get to 8 from 3, does the same pattern get you to 14 from 5? It's not trivial. So here's what I typically will do. Like if I'm clueless about it, sometimes you'll have a hint of what to do, but if you're clueless and you're like, oh, I don't know what the pattern is, you try some things. So here are some standard things. I'm going to look at 2 times the index. I'm going to look at 3 times the index. I'm going to look at the index squared. I'm going to look at the square root of the index. Like you just sort of look for patterns and in any of these calc books, the patterns are going to be with sort of basic things. There's not going to be like, you know, some weird function tossed in there. It's going to be something fairly routine. And let's just see if we start to see a pattern with any of these. So here we're just going to double the index value. Look over here at our a sub n, say, do we see a pattern? There's no obvious pattern is jumping out. Let's go to 3 times n. We get 6, 15. I'm not multiplying very good there. Multiplying n, so I should have 3, 6, 9, 12, 15. And then we ask ourselves, do we see a pattern there? What do you think with 3n? Do we see a pattern with the 3n and the a sub n?
Yes.
Yeah. Right? It jumps out. Once it's there, it jumps out at you. You're like, oh, look. 3 is 1 more than 2. 6 is 1 more than 5. 9 is 1 more than 8. 12 is 1 more than 11, etc. Once there's a pattern, it's pretty obvious. And so you're just trying to figure out what function is giving us the pattern. These ones are not going to work in this particular case, but those are common things to try. And so what we see pretty easily now is, oh, you are freaking kidding me. They came in and fixed it before break. OMG. So what is the a sub n that we are, what is the function then? So for part C, we're going to have a sub n is going to be, 3n minus 1. So that is going to be our function. So you all start working on this one. So 64, 32, etc. So write that down. And then I will hit restart on this miserable machine. Yeah, I can't even control Alt Delete. When you can't control Alt Delete, all right, so let's see if we can piece that second one together. So we said this one, a sub n is 3n minus 1. Okay. Okay, so setting up our table here for this one, we want to make the observation that we're seeing powers of 2. And so I'm going to write off to the side here, this is 2 to the 6, this is 2 to the 5, this is 2 to the 4, that one is 2 to the 3, that one is 2 to the 2, etc. And so let's get our n values in here. So n is 1, 2, 3, 4, 5. And let's just throw in some powers of 2. So this is 2 to the 1, this is 2 to the 2, this is 2 to the 3, this is 2 to the 4, this is 2 to the 5. So we can write that as 2. Think of that as 2. Think of it like this. All right. Now, any ideas? Do we see a pattern here? If you look here, what is true about the sum of all these powers? So they all add up to 7. And so if we say this, so if we say 2 to the, let's see, what do you think we're going to do up here? I think I heard somebody say it. 7 minus n, is that what you just said? So if we subtract off the n, so if they add up to 7, if we subtract 1 from 7, we'll get a 6. If we subtract 2 from 7, we'll get a 5. If we subtract 3 from 7, we'll get a 4, etc. So that is going to give it to us. That will be our explicit formula. So this will be the functional representation. Plug in n equals 1, we're going to get that. Plug in n equals 2, we're going to get 2 to the 5. Plug in n equals 3, and we're going to get all the way down. Does that make sense? So setting up a table in some way, and using observations like, oh yeah, these are all powers of 2. Any question on that? And it will keep working, as we go higher. These numbers will start to become fractions, a half, and then a fourth, and then an eighth, and it will still be powers of 2. 1/8 is 2 to the negative 3. So for these first two, we found writing the recurrence relation easier than writing the explicit formula. How about this one here? So for this one, certainly the terms are suggestive. What do you think the next term is going to be?
36.
36. Term after that? 49. So we have that. And we probably don't need to write up a table to come up with part C here. You can see that a sub n is perfect square, so it's n squared. So if we put our indices down here, so n is 1, 2, 3. If we put them below the terms, just as a quick note, we can see, oh yeah, if we square 1, we get 1. If we square 2, we get 4, etc. So that is the explicit function. So for this one, it's going to be a little bit harder to come up with our recurrence relation. Let's think about it. So we're going to start with a recurrence relation. We need to have a starting point, so we're going to start with a sub 1 is 1. Now we have to get to a sub 2 from a sub 1. So we want to get to this 4 from this 1. So that from that 1, we have to get over to this 4. And we have to come up with a pattern that's going to work anywhere. So it might be better to look in the middle here. We need to get to the 25 from the 16. If we were down in the indices, we kind of know what to do. It's like, okay, well, if we can get to this 5, we know we just have to square it. How can we sort of track ourselves over to that 5 from the 16 to get to that 25?
N plus 1 squared.
So first we have to take a square root to get to the 4. So if we take the square root of 16, that's going to pop the 4. Then we can add 1 and get to the 5, and then we can square it. So we're going to take the prior term, which is a sub n, take its square root. So if this is a 16, the square root of 16 is a 4. That puts us down into the red numbers here. But then we have to add 1, and then we have to square all that. So that'll be our pattern. So this one a little bit harder to find the recurrence instead of the explicit. Let's check it. Let's check. Let's plug in the 9 here. So if we plug in the 9, square root of 9 is 3. Then we add 1, that brings us to 4, and then we square it and we get to 16. So that's going to be our pattern for that recurrence one. Okay, so let's talk about some more limits. So here we have a sequence. We want the limit of the sequence. So if we write out some terms just to get a visual, we are going to think of, let's see, plugging in 1. What's the first term in this sequence going to be?
9.
9. How about the second term?
99.
99. Right, so we're just plugging in the n value. We have to 10 raised to that index value, so that's going to be 100 minus 1 is 99, and we can see the pattern pretty quickly. So here are the first 4 terms of the sequence. Looking at that sequence, it becomes pretty obvious that the limit of a sub n as n goes to infinity is infinity. Right, these sequence values are getting arbitrarily large. There is no bound. So this is another one of those sort of, if we look right here, another one of those Calc 1 basic limits. If you have a base that's larger than 1, and you let the exponent go to infinity, where is that going to go? To infinity. 2 to the n is going to go to infinity. If you start multiplying a number bigger than 1 by itself, that goes to infinity. 2 times 2 is 4, 4 times 2, it goes up without bound. If the base were less than 1, say 1/3, 1/3 to the n is going to go to 0. If you take a number less than 1 and multiply it by itself repeatedly, it gets smaller and smaller and smaller and smaller. 1/3 times 1/3 is a 9th, and 9th times 1/3 is a 27th, right? So less than 1 multiplication is going to take you to 0. Bigger than 1 is going to take you to infinity. So that's one of those basic limits. If the base is bigger than 1, it's going to go to infinity. Now let's look at this one. So here we have a sub n is 1 minus 10 to the negative n. And I did this over here in Desmos. You can see that the first term, if we plug in a 1, we have 1 minus 1/10, which is 0.9, 1 minus a tenth. If we plug in a 2, 10 to the negative 2 is 1 over 10 to the 2, so it's 1/100th. So 1 minus 100th is 0.99. So here are the subsequent terms as we keep subtracting off less and less from 1. So as we subtract off less and less from 1, looking at the graph, we see, oh, the limit. We can either look at the graph, we can look at the table feature in Desmos, and you can see that we're getting closer and closer to 1. Okay, so that limit is going to be 1. When you do this more analytically, if we take the limit of a sub n as n goes to infinity, this is the limit of that. And here's where a handful of you screwed up on the exam. This negative exponent, you do not need to make it a positive exponent, but for 99% of students, it's way easier to evaluate limits when you have no negative exponents. So if you rewrite it like that, it becomes more obvious. As n is going to infinity, this denominator is growing without bound. And if the denominator is growing without bound and the numerator is a constant, the fractions are going to 0. So it's a good strategy to get rid of the negative exponents because it becomes it's just easier to analyze. Just almost always is easier for most people. And so we also know that the limit of a constant is that constant. Limit of a constant is a constant. So this value will be 1. So we've got all 3 ways of doing this limit. We can look at it graphically, we can look at a table, we can look at it analytically. So lots of reinforcement. Any questions on any of the steps there in finding the limit of that sequence? So we've just changed one word. In Calc 1, you found limits of functions. We're finding limits of sequences. It's the only difference, but you're doing them the same way. And a sequence, again, is a function. So not a huge stretch, but we definitely want some practice. Let's look at taking the limit of a recursive sequence. So these recursive ones are a little finicky. And typically what you want to do with a recursive sequence is write out a bunch of terms first. And so what I see, I did it in Desmos there, and what we're seeing is that, okay, when we're at 1, plug in a 1 down there, a sub 1 is 1, now we plug that in to get a sub 2. So we start with a 1, and then we get a sub 2 is 10. And then we plug in a 10. 10 divided by 10 is 1. Then we plug in a 1, and we get 10. And so we can see that this sequence is just bouncing back and forth between 10 and 1. 1, 10, 1, 10, 1, 10, 1, 10. So that tells us that the limit of this sequence is what? Does not exist. And we can't write 1, of course, because the terms aren't getting closer and closer and closer to 1. We can't write 10 because they're not getting closer and closer and closer to 10. And we can't write infinity, so the only thing we would write is d and e. This is the only thing that makes sense to write there. Yeah. If we did have a sequence that was constant, remember, so if our sequence was just say 2, 2, 2, 2, etc., then the limit here is 2. So the terms, when we say getting closer and closer to a single number, by default, this sequence satisfies that condition. We're as close as we can possibly get to 2, repeatedly. Okay. Now, So for a recurrent sequence that diverges, okay, we see this pattern here. Now this one is going to converge. We can see that all the values are 2. All right, so the sequence starts at 2, and every time you plug in the prior term, you end up with 2 again. So if we look here, we could say, okay, the limit is 2. Now, that's not very analytic, though. We just sort of created the terms, and we know that the limit of a constant sequence is itself. Let's do this in a slightly different way, though. Let's do it in a more analytic way. So when you look at a recurrent sequence and you suspect that it converges, there is a strategy that you can use. To show divergence, all you can do is list the terms. This technique that we're about to do only works if the sequence does in fact converge. Here is what we do. So we assume that the sequence converges. So we're going to assume that the limit of a sub n is equal to L as n goes to infinity. We don't know what L is yet, though. We just assume it's going to converge. And the way we come to that conclusion is by looking at data. And we say, oh yeah, it looks like the limit does exist. We have to have very convincing evidence that it converges. And if we have very convincing evidence that it converges, we can find L with the following technique. So we're going to take our recurrence relation here, and we are going to take the limit of both sides. So we're going to take the limit of both sides of this. So we look at that recurrence relation, and we just take the limit of both sides. And we only do this. This is key here, that we only do this if we are darn sure that the limit exists by looking at empirical data. So we're assuming that the limit exists, and we're just trying to find L. Now, when we take the limit of these two sides, we are trying to take the limit of this sequence and this sequence. And in this step, we can kind of think of each of those sequences as different. We can say, okay, we're looking at the limit of this sequence over here. N is starting at 1, right? N starts at 1. The first term in the sequence is a sub 1. So over here, this sequence is a sub 1, a sub 2, a sub 3, a sub 4, etc. This side, though, has one less term. Right? N starts at 1. So this one, first term is a sub 1, second is a sub 2. This sequence, if we think of this sequence as distinct from that, it's the same exact sequence, except this starts with a sub 2, because n equals 1 is where we're beginning. This right here is for n equals 1 and beyond. A sub 0, this one they started at 0. So a sub 0 is 2, and then a sub 1 is going to be also 2, but it's going to be defined from that a sub 0. So the main point here is that this sequence is the same as that sequence, except it has one less term. That's it. So they have the same limit. Right? If you have two sequences that have the same tail, and the front numbers are a little different, the limit's the same. For example, if we have this sequence that's 100, and then 1, 1, 1, 1, etc., and then this sequence that is, let's suppose this sequence is 100, 90, 50, 1, 1, 1, 1, etc. Don't those have the same limit? Like, the important thing when you're taking a limit is as n goes to infinity, and so it says as you get further and further out in the sequence, are you approaching a single number? Yeah, in both those cases, we're approaching the single number of 1. The leading terms have no bearing on the limit. So we just have to look at the tail. So that's the idea here, is that if If this just has one less term, it doesn't matter. Both of these have the same tail. We said that the limit of a sub n is L, so that means the limit of this one is also L. So this just creates a little algebra here. And we get that. The limit of 1 is 1. The limit of a sub n is L. Limit of 2 is 2. Limit of a sub n plus 1 is also L. So we get this little algebra equation. Subtract L over 2 from both sides. Multiply both sides by 2. And that tells us that the limit is 2, which we kind of knew we were going to get anyway. So this technique of finding the limit value, again, only works if the sequence is going to converge. Okay, unless someone has a question, then we'll do a little overview of infinite series. So this first section, we dabble a little bit in sequences, dabble a little bit in series, and then we'll get into finer detail. Okay, so a sequence is just a list of numbers, more precisely an ordered list. So we have, everything is in its own position. We can't jumble it up. Sequence is ordered. Okay, so a series is just a sequence where you add the terms together. So a series is a sum. That's it. So here we have a sequence of terms. There's our sequence of terms. And if we add the sequence of terms, we are getting a series. So we use the Greek letter sigma, capital sigma, for series. S for sum, infinite series. So sigma, this just means to add up all the terms from k equals 1 to infinity. So that's our notation, capital sigma. Now, to analyze an infinite series, we need to create a secondary sequence. We know how to take limits of sequences. Taking limits of sequences is the same as taking a limit of a function. So we know how to do that. And what we have to do is build this secondary sequence. And the secondary sequence is going to be the sequence of partial sums. So what we are doing is creating this new sequence, S sub 1, S sub 2, S sub 3, S sub 4, etc. This new sequence is defined like so. S sub 1 is just the first term. S sub 2 is the sum of the first two terms. S sub 3 is the sum of the first three terms. So we're sort of scaffolding our way to the total sum. So each of these S sub n's are getting closer and closer and closer to the total sum. So we're sort of defining these as partial sums. Right? We're taking a partial sum. S sub 3 is a part of the whole sum. It's the first three terms added together. S sub n, by definition, is the sum of the first n terms in the sequence. So we're going to add these first n terms in the sequence. This is what S sub n is going to look like in sigma notation, in summation notation. And here is our conclusion. So if the sequence of partial sums has a limit of L, then we say the infinite series converges to that limit, and we write the following things. So the infinite series will converge to L if the limit of the sequence of partial sums is L. So if the limit of S sub n is L, then the series converges to L, the series is equal to L, the value of the sum is L. Like, you can say a whole bunch of different things that mean the same thing. All right, so let's pick apart a little example that should be intuitive. So let's suppose we have this infinite sum. So that's an infinite sum. We've talked a little bit of examples like this. So there's our infinite sum. These are the terms in our sequence. So the sequence of terms would be this. So if we were asked to write out the sequence of terms, the sequence of terms would be as follows. So that's the sequence of terms. Now we're going to build the sequence of partial sums. So the sequence of partial sums will be the first term, OMG. So the first term will be 0.3. What will the second term in the sequence of partial sums be?
0.33.
0.33. And so you can see that our sequence of partial sums is going to be 0.3, 0.33, 0.333, etc. Double check, this is not good. All right, so that sequence of partial sums is what we need to analyze then. I'm listening. So there is our sequence of partial sums. So the limit of S sub n is, I totally agree, is 1/3. So therefore, this is the sum of the series. So how do we do that, though?
There was a MyMathLab problem that did something similar.
And so, do you remember what they did? They might be doing it in a more calculus method. There's an algebra way that
Oh, okay.
I'm hoping
'Cause
that...
they multiply both sides by, or they let x equal 0.333.
Yes.
Multiply both sides by 10x.
Perfect. And that's exactly what we want to do. The algebra technique is going to say, oh, well, let's look at this. And what we want to do is multiply by something that will allow us to basically break apart the right-hand side into a sum. And a decimal is really a plus, right? That really means 3 plus, 0.3 repeating. Right? And then 0.3 repeating is, what did we say 0.3 repeating was to start with? X. So then we subtract x and we get back to a little algebra and we see that, oh yeah, we get 1/3. And so this technique, this algebra technique works anytime we have a repeating decimal expansion. So let's suppose we have this repeating decimal expansion. So we know it's a rational number because it's a repeating decimal. Well, if it's a rational number, it can be written as a ratio. What do you think we're going to multiply both sides by here? 1,000. So we want to multiply by whatever pulls off one of those repeating chunks. So if we multiply by 1,000, we'll end up with that. And then that repeating piece gets replaced with, oh, you are kidding me. All right, let's take our break. So let's finish this one off on the board and then we'll take our break. So we are going to have 1,000x is equal to 125 plus x. So we subtract the x. We get 999x equals 125. So x is going to be $1.25 over 999. That'll be our rational expression. So anytime we need to convert back, we can use this algebra technique. And we will learn in this chapter of another technique. This type of series can't move that, is called a geometric series. So a geometric series is when you have a common multiplier that takes you from one term to the next. When you look at this, when we look at this series here, 0.3 plus 0.03 plus 0.003, etc., do you see what the common multiplier is? What would we multiply this by to get to this? 1/10. And then we would multiply this by 1/10 again to get to that term. So anytime we have a geometric sequence here, or a geometric series if we're adding, then we can do this kind of thing. So that's a geometric pattern. Geometric pattern, we can always do this. And we'll use that as an alternative to the algebra. All right, let's take our 10-minute break, and I will reboot again and call IT. Call IT. What am I going to call them? They said they fixed it. Me.
I think I had like 4. Maybe.
Okay, so this slide here is just sort of another example we're going to look at where we can talk about the different definitions. A lot of dealing with infinite series is getting the terminology straight. The sequence of terms, the sequence of partial sums, those kind of things. So let's consider this number 1/9. If you do long division, you could rewrite 1/9 as a repeating decimal. Here, we're taking our repeating decimal notation and we're writing it as an infinite sum, infinite series, you can say either. So again, let's identify the sequence of terms. So sequence of terms, that's the a sub n's. That will be the sequence of terms. And if we wrote it out as a series, we would write it like this. So now we have it written as an infinite series. So we take our sequence of terms, we add up the sequence of terms to form the series, and then we have to build the sequence of partial sums. So the sequence of partial sums, the first term is just the first term. The second term in the sequence of partial sums is the sum of the first two. And so we do this repeated addition where we start with the first term, and then we go to the first two, and then we go to the first three. And that's the sequence that we analyze. If that sequence has a limit, then the series converges to whatever the limit of that sequence is. All right. And so here's just a picture of a series. So this is the sequence of partial sums. And that sequence of partial sums is converging to this value right here, which of course is 1/9 where we started. So 1/9 is the value of the series. It is the limit of the sequence of partial sums. And 1/9 can be written as 1.1 repeating. And we could find, if we had the 0.1 repeating, we would do the same thing that we did a minute ago. If we wanted to convert that to a rational function, we do the multiplication by 10. And then we would have 10x equals 1 plus x. And then we would have 9x is equal to 1, so x is 1/9. So anytime we have a repeater, we can go over to the fraction by doing that, using that algebra process. So terminology, super important. All right, let's come in here. So for the following infinite series, find the first 4 terms of the sequence of partial sums and then make a conjecture about the value of the series. Okay, we've already talked about this quite a bit. So this sequence, the sequence of partial sums, is going to look like that. And what is the limit of S sub n?
2/3.
Limit of S sub n is going to be 2/3 as n goes to infinity. So in other words, what we would say is that this series equals 2/3 it converges to 2/3, its value is 2/3, whatever we want to say. So we just have to remember there are three things: sequence of terms, sum of terms, sequence of partial sums. So three big identities, three big things to identify. Okay, how about this series? So again, we have a series, and in math, when we say series, we mean infinite series. We will look at finite series, but if it's a finite series, you're going to be explicitly told. So if you just hear the word series or sequence in math, you automatically assume infinite sequence, infinite series. If we had a finite sequence or a finite series, we would be explicitly told. So this series of partial sums will be 4, and then 4.9, and then 4.99. And then, yeah, you get the point. And what do we think the limit of this S sub n is?
5.
The limit of S sub n as n goes to infinity is going to be 5. So that sequence is getting arbitrarily close to 5. So the limit of that will be 5. Now, and again, we can use the algebra technique here. If we let x equal 4.9 repeating, we just do, we'll do the same thing. We'll multiply by 10, blah, 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 and it will work out fine. Okay, next slide, which I can't see. Can't see the next slide.
Did you turn off the big screen?
Wow. Nothing's working. Can't see anything.
It's something that's no contest.
Sequence here, we don't know where it's converging. So when we look at, let's see, that's recording. Okay. So here's our sequence of partial sums, right down here. I guess I haven't written it out yet, so let's write that out. So when we look at our sequence of partial sums, we have a half, comma 3/4, comma 7/8, comma 15/16, etc. There's no way to decide what that converges to just by looking at it. The only way we can find the limit of this sequence is if we have a numerical expression, if we write S sub n as a function, if we have some explicit formula for it. In general, it's very difficult to find an explicit formula, but there are some for which we can. And let's see if we can here. So when we look at S sub n, let's see if we can find a pattern here. First, let me have you focus in the denominator. Can we come up with a pattern to get to this denominator from this index value, this denominator from that index value, that from that? Do we see our pattern for that denominator?
2 to the n.
2 to the n, all right? This is 2 to the 4, this is 2 to the 3, this is 2 to the 2, that's 2 to the 1. So for S sub n, this is going to be 2 to the n. And what do we notice about the numerator in all of these terms here? The numerator, how is it related to the denominator?
It's 1 less.
It's just 1 less. So we can say that that is the numerator for S sub n. So now we have a formula for the nth term for S sub n. We have a formula, and we can find the limit of a formula. We know how to do that. To find the value of our series, we need to take the limit of S sub n. If we can find the limit of S sub n, that tells us the value of our series. And this is very easy. The part that is discouraging is that it's very rare that you can do this. The only type of series that we are going to look at where you can construct a formula for S sub n is this type of series, which is called geometric. And so again, this is geometric because there's a constant multiplier between the terms. What is that constant multiplier? 1/2. So we are doing repeated multiplication by 1/2. So that's what tells us that that series is geometric. You can say the sequence is geometric and that leads to a geometric series. Both are geometric. And so if you have a geometric series, you will be able to find a formula for S sub n, and then we can take the limit of it. Now, let's review a little bit of limit technique here. Any idea what we should do for the next step to evaluate this limit?
Split the fraction.
Split the fraction. So split the fraction, we're going to go like that. We're going to divide the 2 to the n into 2 to the n and get 1 minus 1 over 2 to the n. And what is that limit? 1. The fraction on the right has an exponential growth in the denominator, so that denominator is growing without bound, so the fractions are shrinking to 0. So that piece of it is going to 0, and of course the limit of a constant is that constant. So that is going to be the limit of the sequence of partial sums, which then allows us to conclude that this series has a value of 1. This series will equal 1. Or you could say that the series converges to 1. Doesn't matter. Doesn't matter what expression you want to use. Converging to 1, the value of it's 1, etc. And so here, this is just sort of pointing out that, yeah, it's very hard to find a formula for S sub n. When we can, it's super easy. But if we can't find a formula for S sub n, Maxwell?
I was just going to ask, so you can go back and forth as long as it's geometric. So if you find a sequence that's geometric, that means the
Corresponding series will
The
be
series.
geometric.
and then vice versa.
Yes,
Okay.
exactly. So the sequence of terms and the series will both be geometric. Yeah. And so for a geometric series, we can find an S sub n. Most series we can't. And this is exactly why. So if you could always find S sub n, this content would be simple. When you come down to, let's see, maybe I have it under handouts. If you come over to handouts and you look right here at convergence tests, that is why we have all of this garbage. Because you cannot always, if you could always find a formula for S sub n, you just take the limit and you're done, and series would be we'd be done. Then this chapter would be over and we'd be going on for the rest of our lives without stressing. But because you cannot find S sub n, except in 2 cases, for now we've seen geometric, there's going to be one other case, which is called the telescoping series. So these 2 you can find S sub n. The rest of these, though, the whole point of those is that if you can't find S sub n, you need another way to analyze the series and whether it converges or diverges. And so if you don't have S sub n, that's what the rest of this stuff is for. That's what we spend the next month dealing with. So it would be really ideal if we could always find S sub n, but we can't. But when we can, it's great. Then it's easy. Then we just have to take the limit. Okay, so let's go to the sequence section now, and we'll get a little more practice taking limits. All right, so the first thing is a theorem, and the theorem says this. Let's look at the picture first. So we've got the black continuous curve. That is the continuous function. The red dots are the sequence, and you can think of the sequence as a subset of the function. You can think of the sequence as embedded in the function, however you want to think of it. The sequence is a subset. And this theorem says if you take the limit of this function, so the continuous function, when we see the x, that sort of indicates that we're talking about the continuous function. N usually distinguishes and gives us the discrete, or the sequence itself. So if the limit of the function is L, that necessarily means the limit of the sequence is also L. So the sequence is embedded within the function, and if the function is getting closer and closer to L, the sequence must also be getting closer and closer to L. So if we have a function that has a limit, the embedded sequence must have the same limit. There's no way for the dots to jump off the function. The dots are embedded in the function, so if the limit of the function is L, the limit of the sequence is L. Okay. The converse is not true. So the converse is not true. The converse would say that if the limit of the sequence is L, so is the limit of the continuous function. So that's false. And so here's an example that demonstrates that. So we're going to take this continuous function, cosine of 2 pi times x. So the blue curve is cosine of 2 pi x. That's a continuous function. That's the blue curve right there. If we take a look at this embedded sequence right there, a sub n is cosine of 2 pi n. So cosine of 2 pi is 1. If you go once around the unit, right, cosine of 2 pi, you're on the right side of the circle, cosine is 1. If you start multiplying by n, where n is an integer, 1 time, 2 times, 3 times, 4, you get to the same place every time, cosine of 2 pi n is always 1. And that's what these little black dots are representing. So at 1, cosine of 2 pi times 1, cosine of 2 pi times 2, cosine of 2 pi times 3, cosine of 2 pi times 4, etc. So that sequence that's embedded inside this function has the following limit. The limit of a sub n as n goes to infinity is 1. Because the value of this is 1 for every n. So the sequence a sub n in this case is just 1, 1, etc. So its limit is 1. But clearly that function has no limit. Correct? That blue function that's oscillating, it doesn't get closer and closer to a number. It's just wobbling up and down. Right? The limit of cosine 2 pi x as x goes to infinity, this does not exist. So the sequence, just because there's an embedded sequence that converges, doesn't give you any information about the continuous function that it's inside of. So if the function that's continuous converges, then the embedded sequence must converge. The opposite, the converse, not true. You can find an embedded sequence that converges that doesn't tell you anything about the continuous function. Slowly. Okay. So this should reflect some Calc 1 that you're familiar with. So in Calc 1 it said limit laws for functions. It's the same idea. If you take the limit of a sum or difference, if each of those has a limit, a and b respectively here, then the limit of the sum or difference is the sum or the difference of the limits. So in other words, you can distribute the limit symbol. You can take the limit of a sub n, the limit of b sub n, and do the arithmetic. Similarly, if you have a function that is formed by multiplying c by a sub n, and a sub n converges to a, then the limit of that combination will just be c times capital A. So in other words, constants can be factored out, can be factored into the front of the limit symbol. Or you can think of the limit symbol as passing through the constant. Similar for multiplication, similar for division. The only caveat with division is that, b can't be 0. You can't have the denominator be 0 because that's undefined. So this is going to talk, this just sort of summarizes one of the things we touched on earlier. The limit of a sequence is determined by the terms in the tail. Like, it does not matter how much crazy business is going on in the first 5 million terms. What matters is the tail. And so you can chop off any number of terms you want, and it has no effect on the limit of that sequence. Okay. Now, so it doesn't matter what the index starts at, because when we find the limit, all that matters is what's going on way, way far away. Now, this is a little different when you talk about a series. When you think about a series, you're adding up all the terms in your sequence of terms. And if you chop terms out of a sum, that changes things. Right? So if you're adding together, so let's suppose we have a series that converges. Let's look at one that we've already looked at. We know this one. So if we chop out some of these terms, okay, we know that that converges to a third. If we ditch the first couple terms and just go with this, this is still going to converge, right? But it's going to converge to a different number. If you chop off these leading terms, yeah, you still get convergence, but if you're adding them together, you've now taken away some of the actual sum. So the convergence is based on the tail, and when we talk about a series, it's actually the leading terms that contribute the most to the actual sum of the series. Right? This is going to converge to a third. 0.3, 3/10 is the biggest chunk of that. And so if we took that away, then this is going to converge to something less. Right, so for a sequence, the leading terms don't matter. But for a series, the leading terms do matter. Okay, some practice with limits. So find the limit of the following sequences or determine that the sequence diverges. In Calc 1, you learned several techniques for evaluating limits. One technique, and most of these techniques are based on our magic bullet principle. Our magic bullet principle, multiplying by 1. Right, we do that a boatload. And this magic bullet technique is the same here. So if we take every term in our expression and multiply it or divide it by the same quantity, we have preserved equality. And what you typically did in Calc 1 and what typically works best is if you divide by the highest power of n throughout the expression. So if we divide everything by n to the 12, what we've really done is multiplied by 1. Does everybody see that we've multiplied by 1? Like, if you were to factor out this 1 over n to the 12 in the numerator and factor out the 1 over n to the 12 in the denominator, that's just 1. Right? So it's another multiplication by 1. That is our magic bullet. It works so frequently. So this is going to become the limit. N to the 12 over n to the 12 is 1. here we get 3. And then here we still have the end of the 12. And our laws of limits, we never actually write this out in gory detail because it's so ridiculous, but it's good to think about. The limit of this fraction, we take the limit of the numerator. The limit of the numerator is the limit of a constant, so that's just 1. And then we take the limit and we push it into the denominator, and we have the limit of a sum, which is a sum of limits. So we take the limit of 3, oh, that's 3, the limit of a constant is itself. And then how about the limit of this little fraction here? 0. So that'll give us 1/3. So that limit is our basic limit, constant numerator, denominator's blowing up, so the fractions are shrinking to 0. So that limit is 1/3. All right. And there's different ways to manage this division. Some books, some teachers will say divide by the highest power of n. Some will say divide by the highest power of n in the denominator. It doesn't really matter. Both will work. Let's take a look at this one. So again, let's go ahead and divide by something. And do we want to divide by the highest power of n? Let's just do that. Let's divide by the highest power of n that we see. That's kind of a simple rule to remember. So if we divide everything by n to the 5th. So let me just sort of write this out, and then I'll put in the division by n to the 5th. So if you do the same thing to every term, you are multiplying by 1. So if we do the same thing to every term, we are multiplying by 1. Because if you factored out 1 over n to the 5th in the top, and you factored out 1 over n to the 5th in the bottom, you would have 1. Okay, so this is going to be limit. In the numerator, we're going to have 1 plus 3 over n to the 4th. In the denominator, we're going to have 10 over n squared and 1 over n to the 4th. Okay, so where does this fraction go? 3 over n to the 4th as n goes to infinity. 0. And do you agree both of these are going to 0 also?
Yes.
All right, so we are now we now have a situation where the numerator is fixed at 1. The limit of the numerator is 1. And the denominator is getting closer and closer to 0. So numerator is at 1. Denominator is getting smaller and smaller, closer and closer to 0. Is the denominator positive, negative, or ambiguous?
Positive.
Positive. So we are always dividing by a positive number that's getting closer and closer to 0. So numerator is at 1, denominator is at 1/10, which would, and then it's 1/100th, and then it's 1,000th, and then it's 1/10,000th. And so that whole fraction is doing what then? Getting larger and larger and larger, right? As that denominator gets closer to 0, the fractions are going to be growing without bound. But always positive. So this limit we write this way. It's positive. You don't have to put the positive, but is going to be infinity. Right? And it's not ambiguous, though. It's not like we don't have sometimes it's positive, sometimes it's negative. Right? We're always positive because n is going to positive infinity, so we're dealing with positive numbers. Okay. So that works great. You could also, if you wanted, you could just divide by the highest power of n in the denominator. A lot of times in Calc 1, you'll have teachers that don't want the denominator to be 0 in the limit process because to analyze it, it takes a little bit more finesse. So if you divide just by the highest power of n in the denominator, you could end up with this. Let's just write it out in So if we divide it by n cubed, so we're dividing everything by n cubed. If we divide everything by n cubed, we would end up with that. And each of these will be going to 0. This one will be going to positive infinity. And the denominator is fixed at 10. So now the denominator is 10, but the numerator is going off to infinity, so the overall limit will be infinity. Either technique works fine. This is what some teachers would prefer because it's just a little easier to analyze when the numerator is going to infinity than when the denominator is going to 0. Okay, arctangent of n. So the limit of arctan of n as n goes to infinity. We know that arctan of x is a continuous function that has a limit. So the continuous function, we replace the n with an x, that's a continuous function. This we know, we've analyzed this already, that limit is
Pi over 2.
pi divided by 2. And so there's that theorem. We already know what the continuous function does. We've looked at that graph a bazillion times. We know that that graph has a limit of pi over 2. So the function is embedded inside here, and that function has to go to the same value that the continuous function goes to. So pi over 2. Treading gently here. This is going to bring back some not so fond memories. When you were in college algebra, or the equivalent of college algebra, you were asked to look at, or you should have been asked, to look at this interesting case. Right there. Back then they called it horizontal asymptotes. We call them limits in calculus, called limit at infinity. And you were asked to analyze this. And we talked a little bit earlier. If we raised 0.9 to the n and took the limit as n went to infinity, that went to, if you take a number less than 1 and repeatedly multiply it by itself, you go to 0. Right? 0.9 times 0.9 is 0.81. 0.81 times 0.9 is going to be 0.7 something. So a number less than 1 is going to go to 0 as n goes to infinity. A number larger than 1 is going to go to infinity. If you take a number larger than 1 and repeatedly multiply it by itself, it will grow without a bound. It's just going to go towards infinity. So in college algebra, usually you look at this thing graphically. And you're looking at it and you're saying, well, heck, as n goes to infinity, 1 over n is going to 0. So this is going to the, we call it an indeterminate form. This is going to the indeterminate form 1 to the infinity. It's indeterminate. It would be so nice if 1 to the infinity was 1, but it's not. Or it can be, it's not always. And then, it's interesting to look at this. Isn't the base always bigger than 1? Right? 1 plus 1 over n. 1 over n is a positive number. No matter how big n gets, 1 over n is still positive. And if you add that to 1, you have a base that's bigger than 1. So it's super tempting to say, oh, the base is always bigger than 1, so this limit should be infinity. Right? That's, most people, when they first look at this, that's what your conclusion might be. If someone said, on the spot, does that go, what do you think that limit is? It feels like it should be infinity, because the base is always bigger than 1, and we know this. But it's not. What is the limit of this as n goes to infinity?
E?
E. That is where E comes from. And you first saw it in college algebra. You were doing the compound interest stuff and, PERT. That is E. And the way that you show that that is E in college algebra, you just graphed it. So that limit is E. And the way you do it in calculus is by using the log limit process. So let's do that one first, actually. Let's come to the bottom of this page and do that one just because it's such a classic. So we want the limit as n goes to infinity, 1 plus 1 over n to the n. And let's just show that that's going to be E. Actually, let's be a little more general. Let's be a little more general. I'm going to make this a over n, and I'm going to put a bn as the exponent. So it still has the form of 1 to the infinity. The base still goes to 1 as n goes to infinity, and the exponent still goes to infinity. So it is a 1 to the infinity thing, a 1 to the infinity indeterminate form. So here is what we do. We are going to call this a function, whatever you want. I am going to change the n to an x because at some point we are going to need to take a derivative. And it's totally fine if you leave it as n. But in your mind, remember that n means discrete. And does a discrete function, like a sequence, have a derivative? Derivatives are based on functions not only being continuous, but they also have to be smooth. There can't be corners or weird things. And a sequence, obviously, is not continuous. And so what we're going to use is that theorem, that if we convert to this continuous function, our sequence is a subset. And if the continuous function has a limit, then the sequence also has the same limit. Okay. So that's why I'm switching to x. When you're doing your homework and you're doing your test, I don't care if you leave it as an n, but I just can't do it. I have to go to x. Okay, so they call this the log limit process for a reason, because we are going to use both logs and limits. So the next step is to take the natural log of both sides. So we take the natural log of the left, we take the natural log of the right, and logs have a property that allow us to take exponents and they can jump in front as coefficients. So that exponent of bx can jump down in front as a coefficient. That's the power rule for logs. All right. Now, so we've said that this original, we're calling this original, oh, I have it right there. This original thing is y, but we need the limit of that. So what we are going to do is take the limit of both sides. And on the left side, when we take the limit can move through continuous functions. One of the limit superpowers is that it can move inside of a continuous function. We've already started seeing that today. When you take the limit of a fraction, you take the limit of the top, the limit of the bottom. Like the limit can jump through things. So it can jump right through this log function, can jump through continuous functions. And so this limit is now as x goes to infinity. All right, so over here we just have what we have. So that's where we're at. So our whole goal is to solve, right, there's y, that thing, and we want the limit of that thing. So this is what our end goal is, to figure out that right there. So I'm just highlighting this to remind you at the very end, we need to get rid of this log here. We need to exponentiate both sides because our goal is to figure out what the limit of y is. That's our goal. So now on the right side of the equation, if you think about what's happening here, this bx as x goes to infinity, that's going to infinity. And where is this going, the quantity inside the log? That's going to 1, because a divided by x as x goes to infinity is 0, 1 plus 0 is 1. And what's natural log of 1?
0.
0. So this whole thing right here is going to 0. That's an indeterminate form. Infinity times 0 is indeterminate. We don't know whether this thing goes to 0 faster than this thing goes to infinity or vice versa. Like there's a whole tug-of-war thing going on. Now, in Calc 1, you learned a really cool technique if you had an indeterminate form where you had 0 over 0 or infinity over infinity. L'Hopital's rule. And that's what we want to do. We want to just sort of do a little algebra here to rewrite this in a way that we can use L'Hopital's rule. And so what we can do is this. I'm going to take one of these factors and shove it into the denominator. Doesn't really matter which one you do. Usually it's easiest to take the non-log factor and shove it into the denominator. And we would have that. Right? Dividing by 1 over bx is the same thing as multiplying by bx. And if you divide by a fraction, you multiply by its reciprocal. The reciprocal of 1 over bx is bx. Now we have a scenario. I'm going to start going sideways. Actually, why don't we come up here? Okay. So now the form here is 0 over 0. So I usually do something like that just to be clear. 0 over 0, you can put a little LH for L'Hopital's rule. We're going to use L'Hopital's rule at this stage. So this is going to be the limit. L'Hopital's rule, very different from the quotient rule. L'Hopital's rule says if you have a quotient of functions and both functions are going to 0, the limit of that quotient of functions is equal to the limit of the quotient of derivatives. Which makes perfect sense. If the derivative is the best approximation for a function, the limit of a quotient of functions should be the same as the limit of the quotient of best approximations. Right? The derivative is the best approximation, so if we change this function to its best approximation and that function to its best approximation, the ratio should approach the same thing. So that's the intuition behind L'Hopital's rule. So we're now going to take the derivative of the numerator and put it over the derivative of the denominator, and then take the limit. So the limit of a log is 1 over the inside. So 1 over this, 1 over the inside, multiplied by the derivative of the inside. Derivative of a log, 1 over the inside times the derivative of the inside. The derivative of the inside, just like limits, derivatives can distribute. So the derivative of the inside is the derivative of 1, which is 0, plus the derivative of a over x. When we're taking the derivative of a over x, think of it as a x to the negative 1. So we have a x to the negative 1, and if we were to take its derivative, we bring the minus down, subtract 1. So this would be negative a over x squared. Right? Everybody okay there? Oh, it was a b though. It's a b here. So we think about taking, oh no, I'm inside here. Sorry, I'm in here. So the derivative of a over x, think of it as a x to the negative 1. Negative 1 comes down, subtract 1 from the exponent, get a negative 2. So we get negative a over x squared. Negative a divided by x squared. So that's the derivative of the numerator. Now let's do what I said for the denominator. Derivative of the denominator, I want to write the side stuff over here because I'm terrified that poor little computer can't handle all this writing. So if we have 1 over bx and we want to take its derivative, it's a quotient. You could pull the x up into the numerator if you wanted, but let's just do quotient rule. Quotient rule says low d high, so start in the bottom, low derivative numerator, derivative of a constant is 0, low d high minus high, which is just 1, d low. What is the derivative of bx? Just b. Right? It's a linear function, so the derivative is the coefficient over the denominator squared. And 0 times bx is 0. And it looks like one of the b's will cancel. So we're going to get negative 1 over bx squared. Everyone okay with that? So negative 1 over bx squared. Negative 1 bx squared. All right. Let's do a little, let's get rid of that. Let's shuffle a little. Let's move that denominator up to the numerator. I'm not going to do anything in the numerator yet. Let's just leave it as it is. Let's write very slowly. Let's say a few mantras. Do not crash, do not crash. So we've got that. The minuses smash together and turn into a plus. Let's see, the x squareds will cancel, right? Those will go away. So let's see, what are we left with? We have limit. It's now positive. We have ab in the numerator. In the denominator, we have 1 plus a divided by x. So what is that limit as x goes to infinity? A times b. A times b. Because this little guy here is going to 0. So our overall limit is ab. So now let's focus on the bigger picture. We've got this on the left side. We've got this on the right side. So our conclusion is therefore the limit of y, this is what we're looking for, the limit of that original function is, we have to exponentiate, so we get e to the ab. That is a super important result that we will see quite a bit. So let's go back and just look. So if we have the simplest case where a is 1 and b is 1, we just get e. So if this is 1 plus 1 over n to the n, we're just going to get e to the 1. So e. All right. So if we have the more general scenario where we have a coefficient on top of this n and a coefficient up there, we get e to the product of a times b. So that is how you use the log limit process. And this is the most important one of them all, e to the ab. All right, so let's come back up here. And we want to use that log limit process on that one. So, and again, just let me emphasize over here, this is a 1 and this coefficient up here is a 1. So we get e to the 1. So on the test, you'll be asked to do a log limit one. So the first thing we do is let y equal, and I will always convert to x. Again, you don't have to convert to x if you don't want. But you get that. I guess I should first ask, do you agree that this is 1 to the infinity in terms of its indeterminate form? Do you see that it's 1 to the infinity? The limit of this base, you have polynomials that have the same power, so you can look at their coefficients. So the limit of that is 1, and then the numerator exponent's infinity. So then we take the natural log of both sides. Over here we take the natural log, and simultaneously we can pull that exponent down. So we've got that. Walking on eggshells here. Log limit process, we need to put a limit in here. And so on the left side, we can move the limit inside the log. And so this will be the limit as x goes to infinity. On this side, limit as x goes to infinity. And I'm going to do this in one step. I'm taking the limit of both sides, but I'm also knowing that I want to put it into a form that can be evaluated with L'Hopital's rule. So now we have, I guess I can keep going this way. Now we have a 0 over 0, correct? So let's make sure we understand. So down below, limit as x goes to infinity, that's certainly 0. Up here, we have a polynomial over a polynomial. They have the same power and the same coefficient. So that means that limit is 1. Natural log of 1 is 0. So now we use L'Hopital's rule. Take the derivative of the numerator, the derivative of the denominator, and reevaluate the limit. So the denominator's derivative, we get negative 1 over x squared. X to the negative 1, negative x to the negative 2. The numerator's derivative, derivative of a log, 1 over the inside. Okay, so we flip the inside, 1 over the inside. Multiplied by the derivative of the inside. The inside is a quotient, so the derivative of the inside is calculated with the quotient rule. So the quotient rule, right here, we're going to do low d high, derivative of the numerator is just 1, low d high, minus high d low. Derivative of the denominator is 1. So high d low minus, low d high minus high d low over low squared. However you remember the quotient rule. Low d high minus high d low over low squared, or some other variation of that. Okay. Let's rewrite this mess and see if we can get somewhere. So we have limit. We're going to do a couple steps at once. So we have that. And then up here, isn't this just x plus 5 minus x? Isn't that just 5? So that's 5 over x plus 5 squared times negative x squared over 1. So here, we can do some cancellation. We see that 1x plus 5 is going to turn that exponent into a 1. So one factor of x plus 5 gets canceled out. And we also see that one factor of x right there is going to take that exponent away and turn it to a 1. And let's just rewrite that one more time before we take the limit. So we're left with minus 5x in the numerator and 1x plus 5 in the denominator. And that limit is?
0.
No.
Infinity over infinity.
Yep.
Which doesn't exist.
You gotta use
Which is
L'Hopital.
indeterminate.
You gotta use L'Hopital again.
So you could use L'Hopital again. So you have two choices. So one is to remember from algebra, they just had you remember that if polynomials had equal powers, you looked at the coefficients, the ratio of coefficients. So the limit would be negative 5. Actually, there's three ways. We could do that. Remember that, oh, they have the same power. They're both linear. We look at the ratio of coefficients. You could divide everything by the highest power of x. If we divide by x, we would have this. You divide everything by x. And that 5 over x is going to go to 0. So this is also a way. Or you could use L'Hopital's also. L'Hopital's will work absolutely fine. So whichever technique. And think about L'Hopital's for a minute. The derivative of the numerator is -5. The derivative of the denominator is 1. -5 divided by 1 is -5. So that gets us close. We're not all the way to the answer yet. So therefore, the limit of y is
E to the -5.
e to the -5. And that is where we wanted to get to. So that is our limit, e to the -5. All right, let's see, can we add some space in here and not cause it to freeze? I'm going to rewrite this one, and I want you to see if you can tell me the limit instantly. What is the limit of that?
E to the power -4.
Yeah, exactly. So if you rewrite it like this, you can see pretty easily that with our format down here, a is -4, b is 1, so this limit's going to be e to the -4. So if you can master this technique, master that formula there, there's a lot of shortcuts here. Now in the exam, I'm going to ask you to use the log limit process. And so, yeah, you can practice it with this one and make sure that you can get to that e to the -4. But once you have that formula down here kind of understood, that's super convenient for a lot of problems. Super convenient. All right, let's take a look at some definitions, some terminology. The word increasing means what you think it means. So a sequence is called increasing if subsequent terms are larger than the prior term. Sequence is increasing. So we've got a couple of weird ones here. Non-decreasing and non-increasing. In math, there is this push to assume the least possible in any scenario. And so that's what these two things kind of are used for. Non-decreasing means it's not decreasing. That means it's either the same, it's constant, or going up. So non-decreasing, it can stay the same or trend up, but it can never dip. It's always got to be trending up. So you have this type of scenario. It can be flat. Maybe I should use dots. So you can be flat and then trend up, but you can never go. Shouldn't have pulled the pen off the paper. So it can never go down. So non-decreasing means exactly what it says. It's not going down. It's not decreasing. So it's flat or going up. Non-increasing, same thing. It's not increasing, so it's staying flat or going down. Decreasing, again, it is what it says. It's decreasing. So subsequent terms are less than prior terms. So that is a decreasing sequence. That's an increasing sequence. A monotonic just means that it's not oscillating. So monotonic means it's going flat and it can trend up, or it can go flat and trend down and then go flat again, but it can never jump from one to the other. So if it starts to trend up, it has to continue to trend up or stay constant. if it starts to trend down, it can continue to trend down or stay constant, but it can't oscillate. So monotonic means it's trending in one direction. Could be flat or up or down. So that's monotonic. Bounded above means that there's a ceiling. So if you're looking at all the dots in the sequence, there is a ceiling that they don't go beyond. Bounded below, same thing, there's a floor. The dots in the sequence never go below a certain y value. And we say in general that a sequence is bounded if it's got a ceiling and a floor. If the sequence all is happening within this range, then we say that it's bounded. Okay, so is there an example of the next? What's this? I'll go to the next slide. Okay, yeah, this really, I think we just have to stop because it's going to take 2 minutes to reboot. And we got to where we really needed to get to. So that's good. Let's just look at this example then, and then we'll call it. So these two words here, when you see non-decreasing, it's totally fine in your mind if you just think of that as increasing. So if you think of non-decreasing as not going down, just think of it as increasing. For me or you to create a function that does this, is literally flat and then goes up and then is flat and then goes up, do any of you know a function that would have that behavior? Where it's literally flat, not, flat-ish, but literally flat and then going up? No. There is no function you have ever studied that does that. So to create that type of function, you would have to be super creative to try to create a function that literally has flat spots and then is continuous also. So it's totally fine to think about non-decreasing, so not going down, just think of just going up. Those are the types of functions we deal with. They're either increasing or decreasing or possibly constant, but they're not doing these combination type of behaviors. So when we look here, this function is decreasing. It looks flat over here, but it's not. It's flat-ish, but it's not flat. It's decreasing. So this sequence, the red sequence, is decreasing, and it's bounded because it has a ceiling of 2, and it has a floor that appears to be 1. The black sequence is also bounded because it's got a ceiling of 1 and a floor of 0, and it's increasing. Right? So you could also say it's non-decreasing because it's not going down, but just think non-decreasing is increasing. And that is not flat. It may look flat, but it's not flat. So these two obscure words, don't get hung up on them. Think about increasing, think about decreasing. And let me finish with one last comment. If you have a sequence that's decreasing and it's bounded below, there's a floor, it has to have a limit. If it's decreasing and there's a floor, there must be a limit. Similarly, if you have an increasing sequence and there is a ceiling, there has to be a limit. All right, so we'll stop there. This will all be fixed by Thursday.
Theoretically.
And take a look at those answer keys and let me know if you're stuck on any of them. You can email me, you can track me down in the Math Center, you can stay after class. Whatever works best for you.